So we learned about the normal distribution, and then there's certain distributions that we can get from doing computations with the normal distribution that are famous enough we use them quite often. So let's look at those. So first of all, if you have x, which is a normal distribution with mean 0 and 1, and you square it, you'll get what's called a chi-square distribution with 1 degree of freedom. And we would say distributed this little thing. This is the Greek letter chi. Well, and you say it like this, but it's spelled C-H-I, but it sounds like chi. Now, if you have multiple standard normal random variables, and you square each one so you get each one is a chi-square distribution, and then you add them up, however many you add up gives you your degrees of freedom. So you can get, once again, a chi-square distribution with v degrees of freedom. Now for you guys, it's not incredibly important that you remember how we get all of these, but it will be important, or you'll use from now on. If you have a chi-square distribution with v degrees of freedom, you can find your expected value by v, and your variance is 2v. Your possible x values will always be positive values because you squared something to start, so you're always positive. Now it's interesting to note that this is definitely not symmetric, but the shape changes based on what v is. So v is your parameter, and so your shape changes based on v, or basically your degrees of freedom. So that's the first one, is a chi-square distribution. The next one is an F distribution. So for an F distribution, what you do is you take two chi-square random variables and divide them each by their degrees of freedom, and then divide that, and you get what's called an F distribution. F distributions are very useful. We use it for quite a few different things, but notice it does have two different degrees of freedom. So that means there's two parameters to help determine the shape. And you can see coming down here and looking at these, again, not symmetric, positive values still, x has to be greater than 0. Here are some different values for degrees of freedom. This tall skinny one, both degrees of freedom are 25, and then we have one here, let's see, one here where they're both 5, and one in the middle where one's 5 and one's 25. So again, all you need to know is that it has 2 degrees of freedom that determine the shape, and that it's not symmetric, positive values. Okay, then you have a t distribution. This one's pretty interesting. You start with the standard normal distribution, normal 0, 1. You divide by the square root of a chi-squared random variable divided by its degrees of freedom. Again, we don't really care about that so much. What we do care about is the shape. Notice the shape. What does it look like? It looks like the normal curve. But slightly fatter, which means it has more variance, or more variability if you prefer. Interesting thing is it's always centered at x equals 0. Okay, you can have positive and negative values. Now here are some different degrees of freedom. So this orange one had 1 degree of freedom, so it's the fattest one. At 2 degrees of freedom, we're getting less fat, 5 degrees of freedom, and then in infinity degrees of freedom, it actually looks a lot like the normal curve. Okay. So again, the t distribution has a shape like a normal curve, but it's a little bit flatter, or flatter means shorter, and then hence fatter, because the variance is slightly larger. But as you get closer to infinity, your t distribution gets closer and closer to a standard normal distribution. We can see that in this applet, where the red line is our t distribution, the blue line is our normal curve. Right now we have a t distribution with 1 degree of freedom. But watch what happens as I move those degrees of freedom and they get bigger. That red curve gets closer and closer and closer to the normal curve. By the time you get to 30, you can hardly tell the difference. and from there it just gets closer and closer. So again, at t equals 1, it starts off a little bit shorter and fatter, but for bigger degrees of freedom, it gets closer and closer to the normal curve until you can't even tell the difference.